Mathematicians. Today we see one nice real analysis problem asked in CSIR June 2014. It is a part B problem. Okay, so let f from x to y be a function from a metric space x to another metric space y, and it is given that xn is a Cauchy sequence. Uh, and accordingly we want to say about f of xn. So basically this question is about uh, how a function behave with respect to Cauchy sequences. Like if f is continuous, then f of xn is a Cauchy sequence. So what is that mean? So in the first option they are saying that uh, xn is a Cauchy sequence. Suppose xn is a Cauchy sequence if f is continuous, then f of xn, the sequence f of xn is a Cauchy sequence. So what is the meaning of this statement? This statement means that a continuous function takes Cauchy sequence into Cauchy sequence. Okay, so that is the first option. If f is continuous, then f of xn is a Cauchy sequence in y. Okay, that is the first option. Now again, if to say some option is correct, we have to prove it. Okay, to prove some option is wrong, we enough to give one example. Again, like I download this question paper from internet, so this option is given as correct, but it doesn't mean that it is correct. So we'll work out and see what is the right option. Okay, okay, good. Now first I claim that the first option is wrong. Okay, so if a continuous function need not take Cauchy sequence to Cauchy sequence. So we enough to give one example. So we in this problem you see x and y are arbitrary metric spaces. So we can take any metric space. I take f from open 0 comma 1 with respect to usual metric to R. Okay, so open 0 comma 1 along with the usual metric is a metric space. Okay, we consider that metric here, that metric space here. In codomain we take R with usual metric. Okay, maybe I'll write R with the usual metric. Okay, then I define f of x equal to 1 by x. Okay, now we consider the sequence xn equal to 1 by n. Okay, we know that like it is a very standard problem in real analysis to prove that the sequence 1 by n is a Cauchy sequence. So I hope you know the answer, or you can refer any real analysis textbook like Principles of Mathematical Analysis, Rudin, or Real Methods in Real Analysis, Goldberg, some textbooks. So the sequence 1 by n is a Cauchy sequence. It's a Cauchy sequence in open 0 comma 1. Now we look at its image f of xn. So this is a sequence 1 by n. Its sequence image sequence f of xn. So now the function is 1 by x. So if you put 1 by n in place of x, you get 1 by 1 by n, that is equal to n. Okay, so this sequence is actually sequence n belongs to n. So this is as n belongs to n is a sequence in R, and you can easily prove that this sequence n is not a Cauchy sequence because it is diverges to infinity. Okay, it's not a Cauchy sequence. Okay, so what we have proved, we have given an example of a Cauchy sequence. Whose image is not a Cauchy sequence under a continuous function. Okay, so you notice that this function f of x equal to 1 by x is continuous in open 0 comma 1. Wherever there is a 0, in that domain 1 by x is not continuous, but in open 0 comma 1 0 is not there, therefore f of x equal to 1 by x is a continuous function. is continuous on open 0 comma 1. Okay, so we conclude that the first option, this option is wrong. Okay, next. Okay, for the we'll do the uh, okay, we do the option second. In the second option, they are saying you observe that f is some arbitrary function from a metric space into another metric space. It is not given that it is continuous. Only in the first option they gave it is continuous, but in the second option it is not given it is continuous. So f is just an arbitrary function from a metric space to metric space. And what they are saying in the second option, uh, if f of xn is a Cauchy, then f of xn is always convergent in y. When a Cauchy sequence is convergent, when a Cauchy sequence is always convergent only if this codomain y is a complete metric space. So we take some uh, in metric space which is not complete as y, then we can construct a counter example for 2. So the option second is also false. Again, I'll do. For example, let consider f from open 0 comma 1 with usual metric to open 0 comma 1 with usual metric. Okay, and you take even f of x equal to x. Okay, now I take xn equal to 1 by n uh, uh, in domain. In domain means I take from here. Okay, so what we need, if f of xn is Cauchy, so it is given that f of xn is Cauchy. If in our example f of xn is also 1 by n, which is Cauchy, right? Xn 1 by n is Cauchy. Therefore, f is Cauchy sequence in codomain 0 comma 1. Okay, right. Now what they are saying, if f of xn is Cauchy, then they are saying that it is always convergent in y. But this sequence, see, basically what we want the Cauchy, yeah, to say second option is wrong, you need a Cauchy sequence in domain whose image is a Cauchy sequence, but that Cauchy sequence should not be convergent. So we have taken a Cauchy sequence xn equal to 1 by n in the domain. I have taken the function f of x equal to x. Its image sequence also 1 by n, but it is a Cauchy sequence. But again we are in the 1 by n only. We are in the again we are in the 0 1 domain only. Therefore, 1 by n. Therefore, 1 by n is not convergent. Not convergent in so we know that 1 by n is not convergent in 0 1. Therefore, option 2 is incorrect. Okay, I hope you understand the logic that we are pursuing. So basically they are saying if f of xn is Cauchy, then f of xn is convergent. But we have constructed an example, f of xn is Cauchy, but it is not a convergent sequence. Okay, okay, let's do again we do the fourth option. So fourth option is again we can take I mean fourth option is similar to second option. Why? uh, because so x is a arbitrary metric space, not necessarily complete, and we are um, so x is a arbitrary metric space. We are not assuming it is complete, and we have taken a Cauchy sequence xn in x. Okay, so if a Cauchy sequence, why it is always need, why it has to be convergent. For example, if again we can take for fourth option also we can take uh, if we take we take x equal to 0 comma 1 and the sequence xn equal to 1 by n. Okay, for fourth option also, then xn is a Cauchy sequence, it is not convergent, therefore option 4 is also false. So it's a part B question, one option has to be correct, so option 3 is correct, but we prove it. Why option 3 is correct? Because it is it is one time asked in the Nbhm interview also. It is a very interesting problem. So we'll write out the option 3 clearly. So what we have? We have f from x to y is a function, some function, and we have taken xn Cauchy sequence in x. We have taken a Cauchy sequence in x, and what they are saying in the third option? If f of xn is Cauchy in y, then f is continuous. So they are saying that if f of xn is Cauchy, then f is continuous. Then f is continuous. So continuity they are giving in the conclusion, not as a hypothesis. Okay. So basically what they are saying, you take a function, just a function. So and take a Cauchy sequence in the domain, and its image is also a Cauchy sequence. So if a function takes Cauchy sequence onto a Cauchy sequence, then the function f is continuous. So in the first option, what we saw, a continuous function, whether it takes Cauchy sequence to Cauchy sequence. No, that is not true. A continuous function need not take Cauchy sequence to a Cauchy sequence. But in the third option, we are saying if a function takes Cauchy sequence to Cauchy sequence, then the function is continuous. That is true. Okay, we prove it. Proof. So what we are claiming, first we write the claim. If a function f takes Cauchy sequence into Cauchy sequence, then f is continuous. Okay, of course f is a map between two metric spaces. Okay, so that we assumed x and y are metric spaces. Now we'll prove it. We need a result. That is a very interesting result. uh, so I left prove it. So proof is much simpler. It just follows from the definition of Cauchy sequence and convergence sequence. So a sequence xn converges to a point x in the metric space x if and only if the sequence the sequence so yeah, the sequence xn is converges to a point x in x if and only if the sequence x1 comma x comma x2 comma x comma so x3 comma x. So what I have done, I have a sequence xn, it converges to a point x if and only if. Now I am forming a new sequence. First term from this sequence, second point is this limit point, third point is from again this sequence, again I am putting this point here, then again point from the sequence, then I am putting the limit x. Okay, so this point I am putting it in the alternate places, in the odd places I am putting the sequences. Okay, so in this way I construct a new sequence. So this sequence xn converges to the point x in x if and only if the sequence this sequence is Cauchy. So basically what we are saying, this sequence xn converges to this sequence xn converges to x if and only if this sequence is Cauchy. So it is a so you try to prove it. It is a very simple proof only. uh, Maybe I can briefly explain how to do it. So what is the meaning of xn converges to x? If given epsilon greater than 0, there exists a stage n naught belongs to n such that modulus of xn minus x less than epsilon for all n greater than or equal to n naught. That is what means to say the sequence xn converges to the point x. So what it says, however small epsilon you give, I can find a stage such that after that stage, uh, every point in the sequence will be in the epsilon neighborhood of x. Okay, for example, if we imagine the same thing in the real line, so this is my x, so and my sequences goes like this, and I put a epsilon neighborhood around the point x. Then, if suppose this is my sequence, then however small neighborhood I put, the infinitely many points of the sequence will be lies here inside this neighborhood. Okay. Now, what again? We write the definition of Cauchy sequence also. Uh, so xn is said to be Cauchy if given epsilon greater than 0. Again, there exists a stage such that modulus of xn minus xn less than epsilon for all n comma m greater than or equal to n naught. Okay, so how to visualize this? Again, you consider real line. We'll look at real sequence. So now we are saying that uh, suppose my sequence goes like this. What we are saying is, if it is Cauchy, then whatever small epsilon we are given, we can find a stage. Say this is a stage. Okay. So after this stage, if you take any 2 points, say this point and this point, after this, say this is my aleph naught. If I take any 2 points after this stage, their distance is less than epsilon. You take any 2 point here, their distance is less than epsilon. Okay. Now, if we combine these two definitions, we get the proof of this result. Okay. Why? Because um, suppose xn converges to x. So this means that we have this is our x1, x2, x3, x4 and goes on. So closed here, um, whatever epsilon I give, I can find a stage. After that stage, everything will be inside the. So this is my stage n naught. After that, after this stage, everything will be inside the epsilon neighborhood of the point x. Okay. Now we claim that so we assume that xn converges to x, and we claim that this sequence is a Cauchy sequence. So now I claim that this sequence is Cauchy. That means that whatever epsilon is given, I want to find a stage n naught after which any 2 points should be at the distance less than epsilon. Now, since xn converges to x, since xn converges to x, this alternating not this alternate sequence will trivially satisfies the required property of uh, being being Cauchy. Why? Because since xn converges to x, uh, okay, okay, what we are trying to prove? We want this sequence to be a Cauchy sequence. What does it mean? I want to find a stage for whatever epsilon is given. I want to find a stage. After that stage, if I take any 2 point of this sequence, they should be distance less than epsilon. That is what we want to prove. Now, since xn converges to x, I can find a I can find a stage in the sequence. This in the sequence xn, I can find a stage after which all the points in the x neighborhood of epsilon neighborhood of the point x. So basically it means that the same stage whichever existed for the sequence xn, I can use it for this sequence also, so that all the points after this stage in this sequence will be lie in the neighborhood of epsilon. Okay. And conversely, if this sequence is Cauchy, then I can find a stage after which any 2 points is less than epsilon. Now you see this x is always there since it is an even term. So always this will be, this point x will be always here. That means that so since x always stays here, we get the definition of we get the condition for xn converges to x. So I have just given a rough idea only, like I but yeah, you just try to see it why it is true and try to write a rigorous proof. Okay, now we use this result to prove that why if a sequence preserves Cauchy sequences has to be continuous function. So we prove it. So we take the sequence criterion for the continuous function, that is f from x to y, and I take x belongs to x. F is continuous at x, the point x, if whenever a sequence xn converges to x, then we want the sequence f of xn to converges to f of x. Then such the function f is continuous at x. This is what we want to prove. Okay. Okay. Now, okay. Fix, you take x belongs to x. I claim that f is continuous at x. Okay. What I know? I know that f, we know what is given. It is given that f preserves the Cauchy sequence. That means that it takes Cauchy sequence to Cauchy sequence. Okay, using that condition, we want to prove that if xn tend to x, then f of xn. Using this result, we want to prove that if xn tend to x, then f of xn tend to f of x. Okay, so now xn tend to x if and only if x1, x, x2, x, etc., etc. This sequence is Cauchy. That is what we proved, right? If and only if, by our assumption, it is given that f preserves the Cauchy sequence. That means that if you look at the image sequence, f of x1, f of x, f of x2, f of x. You look at this sequence. This sequence is Cauchy. Why? Because this sequence is Cauchy. This is the image sequence. Okay, this is one. So if by our assumption, if this is Cauchy, then this is also Cauchy. Okay. Again, this sequence, is Cauchy. You see, in the even places, f of x is there. So whenever you have a sequence like this in even places, there is a number, and in odd places there is a sequence. If and only if we get we get this sequence f of x and converges to f of x. Okay, so this is again by using our this main result. So sequence xn converges to x if and only if this alternate sequence is a Cauchy sequence. So here we are using the same result, f of x1, f of x, f of x2, f of x, etc., etc. This sequence is Cauchy, therefore f of xn converges to f of x. Therefore we get therefore f is continuous at x. Okay, so we have concluded that whenever a function preserves the Cauchy sequence, then the function has to be continuous. Okay, I hope you understand this problem. If you have any doubts, do let me know in the comments. Have a good day. Thank you.